What if everything you have ever touched, every star you have ever seen, and even your own thoughts are not made of particles at all, but of something far stranger, something that quietly vibrates beneath reality, unseen and almost impossible to imagine? There is a growing idea in physics that what we call matter may not truly exist in the way we think. That electrons, quarks, and even light itself are not tiny points floating in space, but instead are different notes played on invisible strings, endlessly oscillating in a hidden layer of the universe. And if that idea is true, then reality is not built from objects, but from motion, from vibration, from something more like music than matter. Here on Velarin's Sleepy Space Mysteries, we've gently explored ideas like hidden dimensions and the strange geometry of the cosmos before. But tonight we take a deeper step, because string theory does not just change how the universe works. It changes what the universe is. It raises quiet questions that linger in the background of everything we know. Why do particles behave the way they do? Why does gravity refuse to fit into our equations? And perhaps most unsettling of all, are we seeing reality as it truly is, or just a simplified surface of something far more complex? So as you settle in, allow your thoughts to slow and imagine for a moment that the entire universe is woven from threads too small to ever be seen, yet responsible for everything. If you enjoy these calm journeys into cosmic mystery, consider subscribing, liking the video, and turning on the bell so you never miss a quiet exploration. You can also join as a member to support the channel. And before we begin, let me know in the comments where you're watching from tonight. Now, let's gently begin unraveling the strings beneath reality. For most of modern physics, reality has been described as a collection of tiny, indivisible points. These points, called particles, were thought to be the ultimate building blocks of everything. Electrons, quarks, photons, each one imagined as a perfect, structureless, existing at a precise location in space. It is a simple picture, and for a long time it worked remarkably well. It allowed physicists to predict interactions, build technologies, and uncover patterns hidden deep within matter. But beneath this apparent success, something subtle and troubling began to emerge. When scientists tried to push this model further, especially into extreme conditions where gravity and quantum mechanics both matter, the idea of point-like particles began to break down. The problem was not philosophical. It was mathematical. When two particles interact, the equations describe them meeting at an exact point in space, an infinitely small location. And at that point, something strange happens. The calculations begin to produce infinities, not just large numbers, but truly unbounded, uncontrollable infinities that make the theory lose its predictive power. At first, physicists found clever ways to work around this. They developed techniques to cancel out these infinities, adjusting the equations in ways that still produced accurate results. This process, known as renormalization, became one of the most powerful tools in quantum field theory. But even with these techniques, there remained a quiet discomfort. It was as if the theory worked not because it was fundamentally correct, but because it was carefully balanced to avoid revealing its deeper flaws. This tension becomes impossible to ignore when gravity enters the picture. Gravity, as described by general relativity, treats space and time not as a fixed stage, but as something dynamic, something that bends and curves. When physicists try to apply quantum rules to gravity using the same point-particle approach, the infinities become far worse. They can no longer be cancelled or controlled. The theory simply collapses under its own contradictions. It is here, in this quiet failure, that a new idea begins to take shape. What if the problem is not in the equations, but in the assumption that particles are points? What if the universe is not built from zero-dimensional objects, but from something slightly extended, something with length? This is where string theory begins. Instead of imagining particles as dots, string theory suggests that the fundamental objects of reality are incredibly small one-dimensional strings. Not strings in the everyday sense, but tiny loops or segments, far smaller than anything we can currently observe. These strings do not sit still. They vibrate, and it is the way they vibrate that determines what we perceive as a particle. In this view, an electron is not a separate object from a photon or a quark. They are all the same thing at a deeper level. They are simply different vibrational patterns of the same underlying string. Much like a single guitar string can produce many different notes depending on how it is played, a single fundamental string can give rise to many different particles depending on its mode of vibration. This shift from points to strings changes everything. When two strings interact, they do not collide at a single point. Instead, they merge and separate over a small region of space and time. The interaction is smooth, continuous, almost gentle compared to the sharp collisions of point particles. And because of this, the troublesome infinities begin to disappear. The equations no longer break down in the same way. The theory becomes more stable, more consistent, as if it is finally aligned with something deeper. But this raises a new question, one that lingers quietly beneath the surface. If everything is just vibration, then what is actually vibrating? What is the string made of? Or is that question itself misguided? As we move deeper into this idea, another subtle realization begins to form. The concept of a thing may not be fundamental at all. What we call particles, objects, even matter itself might simply be patterns of motion. Temporary expressions of something more basic, something that does not have a fixed identity until it vibrates in a particular way. This perspective is difficult to hold onto at first. It challenges the way we instinctively think about the world. We are used to believing that objects exist independently, that they have properties that belong to them. But in the language of strings, properties like mass and charge are not intrinsic. They emerge from how something moves. And if that is true, then reality is not made of objects, but of behavior. This idea will become even more unsettling as we continue, because once we accept that particles are not fundamental, we are forced to ask a deeper question. If strings are the foundation, then what determines how they vibrate? And where do these vibrations take place? The answer, as we will begin to explore next, leads us into something even stranger. The possibility that the universe has more dimensions than we can perceive, dimensions that quietly shape every vibration, every particle, and every moment of reality itself. If we follow this idea gently, without rushing, something very unusual begins to unfold. The notion that particles are not solid things, but rather different vibrations of a single underlying object, quietly dissolves the boundaries we are used to. What once seemed like a universe filled with many different ingredients begins to look more like a single instrument, playing countless notes. Imagine for a moment a vast cosmic string. Not literally one string stretched across space, but a fundamental type of object that exists everywhere, at every point, at every scale. Now imagine that this string can vibrate in countless ways. Some vibrations are simple and smooth, others are complex and energetic. Each pattern carries a different amount of energy, a different rhythm, a different signature. And from these patterns, everything emerges. A low, steady vibration might appear to us as a particle with very little mass. A sharper, more energetic vibration might appear as something heavier. A certain twisting motion might give rise to what we interpret as electric charge. Another subtle variation might determine how that particle interacts with others. From our perspective, these properties seem fundamental, as if they belong to the particle itself. But in this deeper picture, they are not properties of objects. They are properties of motion. This is one of the quiet revolutions of string theory. It suggests that identity in the universe is not fixed. It is not something inherent. It is something that arises from behavior. The electron is not a permanent, indivisible thing. It is a stable pattern of vibration. And stability, in this sense, is simply a pattern that persists long enough for us to recognize it. This idea begins to blur the line between what is real and what is emergent. Because if particles are just vibrations, then they are not the foundation. They are expressions, temporary configurations of something deeper that we cannot directly observe. And just like a musical note fades when the vibration stops, the existence of a particle depends entirely on the continuation of that pattern. But this leads us to a deeper curiosity. If everything is just vibration, then what determines which vibrations are possible? Why do we observe the specific particles that we do, and not an infinite chaotic mixture of random forms? The answer lies in the rules that govern how strings can move. These rules are not arbitrary. They arise from the fundamental structure of the universe itself. Strings are not free to vibrate in just any way. Their motion is constrained by the geometry of the space they exist in, by the tension within the string, and by the underlying symmetries that shape reality. To understand this more intuitively, imagine again a musical instrument. A guitar string cannot produce just any sound. Its length, its tension, and the way it is fixed at its ends determine the notes it can create. Some frequencies are allowed, others are not. The structure of the system shapes the possibilities. In the same way, the universe acts like a vast, hidden instrument. The strings that underlie reality can only vibrate in certain permitted ways. And those permitted vibrations are what we observe as the particles of physics. The laws of nature, in this sense, are not imposed from outside. They emerge from the allowed patterns of vibration within this deeper framework. This realization introduces a quiet elegance. It suggests that the complexity of the universe, the enormous variety of particles and forces may all arise from a single simple principle. Not from many different building blocks, but from one type of object behaving in many different ways. And yet, as calming as this idea may feel, it carries with it a subtle unease. Because if everything is just vibration, then nothing is truly solid. The sense of permanence we associate with matter begins to dissolve. What we perceive as stable objects, from atoms to mountains, are simply collections of persistent patterns. Patterns that could, in principle, change if the underlying vibrations changed. It also raises another question, one that gently echoes in the background. Where do these vibrations happen? In what kind of space do these strings exist? At first, we might assume the answer is simple. They exist in the same three dimensions we experience every day, along with time. But as physicists began to explore the mathematics of string theory more deeply, something unexpected appeared. The equations refused to remain consistent unless additional dimensions were introduced. Not one or two, but several hidden, compact, and completely invisible to our senses. This is where the story begins to shift from strange to almost unimaginable. Because if the vibrations of strings determine the particles we see, and if those vibrations depend on the structure of space, then the unseen dimensions of the universe may be quietly shaping everything. Every particle, every force, every interaction could be influenced by dimensions we cannot perceive, folded into reality at scales far beyond our reach. And so, as we continue this journey, we begin to move away from the familiar picture of space as something simple and empty. Instead, we approach a vision of reality that is layered, intricate, and deeply hidden. A place where what we see is only a small part of what truly exists. In the next segment, we will explore how one of the greatest mysteries in physics, gravity itself, may not need to be forced into this framework at all. Instead, it may emerge naturally, quietly appearing as an inevitable consequence of these vibrating strings. As we move deeper into this gentle unraveling of reality, one of the most persistent mysteries in physics begins to return to the surface of gravity. It is the force that shapes galaxies, bends light, and anchors us to the Earth. Yet in the world of quantum physics, it remains strangely out of place. For decades, physicists have tried to bring gravity into the same framework that successfully describes all other forces, but every attempt seemed to fracture under pressure. The equations would become unstable, the infinities would return, and the harmony between theories would quietly collapse. But within string theory, something unexpected happens. Gravity does not need to be inserted by hand. It does not need to be forced into the equations. Instead, it appears naturally, almost as if it was always meant to be there. To understand this, we return once more to the idea of vibrating strings. Each vibrational pattern corresponds to what we perceive as a particle. Most of these patterns resemble the familiar particles of physics, electrons, photons, and others. But among these countless possible vibrations, there is one that stands apart. A particular mode of vibration that behaves exactly like the particle physicists have long predicted for gravity. The graviton. The graviton, if it exists, is thought to be a massless particle that carries the force of gravity. In traditional approaches, it must be introduced artificially, and doing so leads to mathematical inconsistencies. But in string theory, this particle is not added. It emerges automatically as part of the string's natural spectrum of vibrations. This is a subtle but profound shift. It suggests that gravity is not separate from the other forces. It is not something that needs its own independent explanation. It is simply one of the many ways a string can vibrate. And if that is true, then gravity is not an external force acting on the universe. It is an intrinsic feature of the universe's most fundamental structure. There is something deeply calming about this idea. The sense that one of the most complex and elusive aspects of reality might arise from the same simple principle that gives rise to everything else. That the bending of space, the motion of planets, and the structure of galaxies all trace back to the quiet oscillations of something unimaginably small. But as always, this realization brings new questions. Why does gravity feel so different from the other forces? Why is it so much weaker? Why does it shape the large-scale structure of the universe, while the other forces dominate the microscopic world? String theory offers a soft and intriguing possibility. It suggests that gravity may not be confined in the same way as other forces. While certain vibrations, those corresponding to particles like electrons and photons, might be restricted to the dimensions we can perceive, the vibration associated with gravity may extend beyond them. In other words, gravity might be spreading into dimensions we cannot see. If this is the case, then its apparent weakness is not because it is inherently small, but because it is diluted. It is shared across a larger space than we are aware of. Like a sound that echoes into hidden chambers, becoming softer as it spreads, gravity may be dispersing through unseen dimensions, leaving only a faint trace within the world we experience. This idea is both elegant and unsettling. It suggests that the force we feel every moment is only a fraction of something larger, something that extends beyond our perception. That the universe may be far more expansive than it appears, not just in distance, but in dimensional depth. And this leads us gently toward one of the most surprising consequences of string theory. For the mathematics to remain consistent, for these vibrations to behave in a stable and coherent way, the universe cannot have just 3 dimensions of space. It must have more, several more, in fact. Dimensions that are not stretched out like the ones we move through, but curled up, hidden, and incredibly small. These extra dimensions are not optional details. They are required. Without them, the theory simply does not hold together. And so, the picture of reality begins to shift once again. No longer a simple stage of 3 dimensions in time, but a layered structure where unseen directions quietly influence everything that exists, where every vibration, every particle, every force is shaped not only by the space we know, but by dimensions folded into the very fabric of existence. It is a strange thought that at every point in space, there may be hidden directions we cannot move through, yet which determine the behavior of everything around us. That the true shape of the universe is not flat or open, but intricately folded, like a delicate geometric structure beyond imagination. As we continue, we will begin to explore these hidden dimensions more closely. how they remain invisible, how they influence the vibrations of strings, and how they may hold the key to why the universe has the properties we observe. And perhaps, as we gently follow this path, we may begin to sense that what we perceive as reality is only a small surface, resting on something far deeper, far quieter, and far more complex than we ever expected. As this picture slowly forms of a universe built not from particles, but from vibrating strings shaped by hidden dimensions, a quiet and almost frustrating question begins to arise. If all of this is true, why haven't we seen it? Why has no experiment ever directly detected a string? Why do our most powerful machines, our deepest observations, still reveal only particles, never the underlying threads? The answer is not that strings are rare or hidden in distant corners of the universe. According to the theory, they are everywhere. They are the foundation of everything. The reason we cannot see them is something far more subtle and far more limiting. Comes down to scale. The size of a fundamental string is believed to be incredibly small. Not just smaller than an atom or even a subatomic particle, but smaller by many orders of magnitude. So small that even if we could zoom in far beyond anything currently imaginable, we would still struggle to perceive it directly. To gently grasp this, imagine trying to see the structure of a single grain of sand from the distance of an entire planet. No matter how sharp your vision is, no matter how carefully you look, the details would remain invisible. Now shrink that grain of sand down again, and again, until it becomes almost inconceivably small. That begins to approach the scale at which strings are thought to exist. Physicists often associate this scale with what is called the Planck length, not as a number to calculate, but as a kind of boundary. A point beyond which our usual ideas of space and distance begin to lose their meaning. At this scale, space itself may no longer behave as a smooth, continuous backdrop. It may become something more granular, more uncertain, more difficult to describe. And strings live at this boundary. This means that to directly observe them, we would need to probe energies far beyond what our current technology can achieve. Particle accelerators, like the most powerful ones on Earth, are capable of exploring incredibly small distances. But even they fall vastly short of the energy required to reveal string-like behavior. So instead of seeing strings directly, we are left with something quieter, indirect hints. We study the patterns of particles, the symmetries in their interactions, the mathematical structures that seem to underlie the laws of physics. And sometimes, in those patterns, we find echoes, subtle suggestions that something deeper may be at work. But there is another layer to this limitation, one that feels almost philosophical. If strings are so small that they can never be directly observed, then how do we know they are real? Or perhaps more gently, what does it mean for something to be real if it can never be seen? In science, there is often a balance between observation and explanation. Some ideas are confirmed directly through experiments and measurements. Others are supported indirectly because they provide a consistent and elegant explanation for what we do observe. String theory currently belongs to the second category. It is a framework that solves problems, that unifies ideas, that brings gravity and quantum mechanics into a single picture. It produces results that are internally consistent, mathematically rich, and deeply connected to other areas of physics. But it has not yet been confirmed through direct evidence. This creates a quiet tension. On one hand, the theory is compelling. It feels as though it reveals something fundamental, something hidden just beneath the surface of reality. On the other hand, it remains beyond our experimental reach. And so, it exists in a delicate space between discovery and imagination. This is not unusual in the history of science. Some of the most powerful ideas have emerged long before the tools existed to test them. The equations of gravity were written before we could measure gravitational waves. The structure of atoms was proposed before we could image them. Understanding often comes first, confirmation later. Still, the scale of string theory presents a deeper challenge. Because it is not just that strings are small. It is that they may be fundamentally inaccessible. That the energy required to probe them might forever remain beyond practical reach. If this is true, then our understanding of the universe may always rely, at least in part, on theories that cannot be directly verified. And yet, there is something quietly beautiful in this limitation. It reminds us that knowledge is not always about seeing. Sometimes, it is about listening to the patterns, the consistencies, the subtle harmonies that emerge from what we can observe. Much like hearing a melody and inferring the instrument behind it, even if we cannot see the strings themselves. As we move forward, this limitation becomes even more significant. Because when we begin to explore how many different ways strings can vibrate, and how many different shapes hidden dimensions can take, we encounter a new and even more unsettling idea. That there may not be just one possible universe described by string theory, but many, an enormous number of possible realities, each with different properties, different particles, and different laws, and among them ours is just one. As we arrive at this point in the journey, something begins to shift again, more quietly, more profoundly than before. Up until now, the idea of string theory may have felt like a deeper explanation of our universe, a hidden layer beneath everything we see. But what emerges next is not just an explanation. It is a multiplication of possibilities. Because once physicists began exploring how strings vibrate within these hidden dimensions, they discovered something unexpected. There is not just one way for the extra dimensions to be shaped. There are many. To understand this gently, imagine that at every point in space, beyond the 3 dimensions we move through, there exist tiny, compact shapes. These shapes are not simple. They are intricate, folded, and complex, like delicate geometric sculptures curled into unimaginably small scales. And the exact form of these shapes determines how strings can vibrate. Different shapes allow different vibrations, and different vibrations produce different particles. Which means that the properties of the universe, the masses of particles, the strengths of forces, even the basic structure of matter, are not fixed by necessity. They depend on the geometry of these hidden dimensions. This is where the idea becomes both fascinating and deeply unsettling. because there is not just one possible geometry. There may be an enormous number of them. Each configuration of these hidden dimensions corresponds to a different version of physics, a different universe, one where particles behave slightly differently or drastically differently, one where forces are stronger or weaker, one where matter forms in unfamiliar ways, or perhaps not at all. This vast collection of possibilities is often described as the landscape. Not a physical landscape we can travel through, but a conceptual one. A space of all the different ways the universe could exist according to the rules of string theory. Each point in this landscape represents a complete, self-consistent universe with its own laws. And the number of these possible universes is not small. It is unimaginably large. So large that even describing it feels difficult. Not thousands, not millions, but numbers so vast they stretch far beyond ordinary intuition. Each one equally valid within the theory. Each one emerging from a different hidden structure of dimensions. And among all of these possibilities, we find ourselves in one particular version. This raises a question that lingers softly, almost like an echo. Why this one? Why does our universe have these specific particles, these specific constants, these specific laws? Are they inevitable, or are they simply one outcome among countless others? String theory, in its current form, does not give a single clear answer. Instead, it opens the door to different ways of thinking. One possibility is that there exists some deeper principle, not yet discovered, that selects one unique configuration from the landscape. A rule that determines why our universe is the way it is, and not any other. Another possibility is more subtle, and perhaps more unsettling, that there is no single chosen universe, that all these possibilities exist in some form, and we find ourselves in this one simply because it allows structures like stars, planets, and observers to emerge. In universes where the conditions are too extreme, too unstable, or too different, nothing like us would exist to notice them. This idea is sometimes referred to as a kind of selection through existence itself. Not a design choice, but a quiet filtering, where only certain kinds of universes can be experienced from within. It is a perspective that shifts the question from why is the universe this way, to something softer. What kinds of universes allow something to ask that question? And yet, even this does not fully resolve the mystery, because the landscape remains vast and largely unexplored. Physicists continue to study different configurations, searching for patterns, for clues, for hints that might narrow the possibilities. But the sheer scale of the landscape makes this task incredibly challenging. It is like standing at the edge of an infinite ocean, knowing that somewhere within it lies the answer, but not knowing where to begin. And so, string theory presents us with a universe that is no longer singular and fixed, but one that is part of a much larger set of possibilities. A reality that may be just one expression among many, shaped by hidden dimensions, guided by subtle geometries, and defined by vibrations we can never directly see. As this realization settles, it gently prepares us for what comes next. Because if there are many possible versions of string theory, and many possible universes, then we are faced with another layer of complexity. There are not just many universes. There are also many versions of the theory itself. Different formulations, different perspectives, all describing the same underlying idea in different ways. And somehow, they are all connected. In the next part of our journey, we will begin to explore these different versions of string theory and the surprising discovery that they may not be separate at all, but reflections of a deeper, unified structure waiting to be understood. Before we drift into that next layer of the mystery, if you're still listening, gently let me know by typing 1 in the comments. As we gently move into this next layer of the mystery, we return to a question that has been quietly forming in the background. If strings are the foundation of reality, and if their vibrations define everything we observe, then what determines how those vibrations behave? The answer, as strange as it may sound, lies not within the strings themselves, but within the space they exist in. Because in string theory, space is not just an empty stage. It is an active participant. Its structure, its shape, and even its hidden features directly influence what is possible. And as physicists explored the mathematics more deeply, they encountered a surprising requirement. The universe cannot have just 3 dimensions of space. For the equations of string theory to remain consistent, stable, and free of contradictions, additional dimensions must exist. Not as a possibility, but as a necessity. Without them, the entire framework begins to unravel. At first, this idea feels almost impossible to accept. We move through 3 dimensions every day, forward and backward, left and right, up and down. We experience time flowing steadily. There is no obvious sign of anything beyond this. And yet, the mathematics insists there is more. Not one extra dimension, but several. In many versions of string theory, there are 6 additional spatial dimensions, making a total of 9 dimensions of space along with time. In other extended frameworks, there may even be more. But these extra dimensions are not like the ones we know. They are not vast and open. They are hidden. To understand how something can exist and yet remain unseen, we can return to a simple image. Imagine looking at a long, thin wire from a distance. It appears as a one-dimensional line. You can only move along its length. But if you come closer, you begin to see that the wire has thickness. There is a circular direction wrapped around it, a second dimension that was invisible from afar. In a similar way, the extra dimensions in string theory are thought to be curled up, compacted into incredibly small shapes at every point in space. They are not stretched out across the universe. They are folded inward, existing at scales so tiny that we cannot directly perceive them. And yet, they are always there. At every location in space, beyond the 3 dimensions we experience, there may be additional directions, tightly wrapped, quietly present, influencing everything without ever revealing themselves directly. This idea transforms our understanding of space itself. It is no longer a simple, empty container. It becomes layered, intricate, almost like a hidden architecture beneath the surface of reality. But the most important consequence is this. The shape of these hidden dimensions determines how strings can vibrate. Each dimension provides a direction in which a string can move or oscillate. And when those dimensions are curled into specific shapes, they restrict and guide those vibrations in very precise ways. The result is that the geometry of these unseen dimensions directly influences the particles we observe. Different shapes produce different physics. If the extra dimensions are shaped one way, strings vibrate in patterns that give rise to the particles and forces we know. If they are shaped differently, the vibrations change, and with them, the entire structure of the universe. This is a subtle but powerful idea. It means that the laws of physics may not be fixed at the most fundamental level. They may be a consequence of geometry, of shape, of the way space itself is folded at scales far beyond our reach. And this leads us back to something we touched on earlier, the landscape of possibilities. Because if there are many possible shapes for these hidden dimensions, then there are many possible ways for strings to vibrate, and therefore many possible versions of reality. But before we move further into that vast landscape, there is something important to understand about these dimensions themselves. They are not random. The shapes that these extra dimensions take are highly constrained. They must satisfy very specific mathematical conditions in order to maintain the delicate balance required by string theory. These shapes are often described using complex geometries, structures that are smooth, symmetrical, and stable in ways that are difficult to visualize. They are sometimes compared to intricate folded spaces, almost like multidimensional origami, where every curve and twist has meaning. And within these shapes, strings move, vibrate, and interact, giving rise to everything we experience. It is a quiet and almost poetic image that beneath the visible universe, beneath particles and forces, beneath even space as we perceive it, there exists a hidden geometry, a silent structure that shapes the vibrations of reality itself. And we, moving through our three-dimensional world, are only aware of the surface of this deeper form. As we continue, we will begin to explore how these hidden dimensions influence the properties of particles in more detail, how mass, charge, and interaction may all emerge from geometry, and how this connection between shape and physics may be one of the most profound insights string theory offers. Because in the end, it suggests something deeply unexpected, that the universe is not just made of things, but of patterns shaped by dimensions we cannot see. As we continue drifting through this deeper layer of understanding, something quietly remarkable begins to take shape. The idea that particles are not fundamental, that they arise from vibrating strings, now extends even further, because those vibrations are not happening in empty space. They are guided, shaped, and constrained by the hidden geometry of extra dimensions. And from this, a new realization begins to emerge. What we call the properties of particles, their mass, their charge, their behavior may not be intrinsic at all. They may be the result of geometry. To understand this gently, imagine again a string. It is free to vibrate, but only within the space available to it. If that space has hidden folds, twists, or loops, then the string's motion becomes more complex. It may wrap around certain directions, oscillate differently depending on curvature, or become restricted in subtle ways. Now imagine that each of these motions corresponds to a different particle. A string vibrating in one pattern appears as an electron, in another pattern as a photon, in another as something heavier, more complex, less stable. But the key is this: those patterns are not chosen randomly. They are determined by the shape of the dimensions the string exists within. This means that if the hidden dimensions were shaped differently, the particles themselves would be different. The mass of an electron, for example, is not just a number assigned to it. In this framework, it emerges from the way a string vibrates within a specific geometric structure. If that structure changed even slightly, the vibration would change, and so would the particle's mass. The same applies to charge, to spin, to the way particles interact with forces. All of these properties begin to look less like fixed attributes and more like consequences. Consequences of how strings move through a deeply structured space. This is where string theory becomes quietly beautiful. It suggests that the complexity we see in the universe, the vast variety of particles and interactions, may not come from many different ingredients. Instead, it may arise from a single underlying object shaped by geometry. In a sense, the universe becomes something like a resonance pattern, a set of allowed vibrations defined by the structure of space itself. But there is another layer to this idea, one that feels even more subtle. Because these hidden dimensions are not simple shapes. They are not circles or spheres in the way we usually imagine geometry. They are far more intricate, multidimensional, folded, and interconnected in ways that are difficult to picture even conceptually. Within these shapes, strings can wind around loops, stretch across curved paths, and interact in ways that depend sensitively on the geometry. Some vibrations may be allowed only if the string wraps around a particular cycle. Others may be suppressed or enhanced depending on how the space is curved. This leads to a kind of filtering effect. Out of all possible vibrations, only certain patterns are stable. Only certain patterns persist long enough to appear as the particles we observe. The rest fade away or never arise at all. And so, the universe we see is not just a random collection of possibilities. It is a selection, a set of stable resonances emerging from a deeper structure. This idea also helps explain something that has long puzzled physicists. Why do the fundamental constants of nature have the values they do? Why does the electron have its specific mass? Why is the strength of electromagnetism what it is? Why do forces behave in precise and consistent ways? In traditional physics, these values are measured, but not explained. They are inputs to the theory, not outcomes. But in string theory, there is the possibility that these constants are not arbitrary. They are determined by the geometry of the hidden dimensions. Change the geometry, and the constants change. This is a powerful shift. It transforms what we thought were fixed features of reality into something dynamic. Something that depends on deeper structure. Something that could, in principle, be different. And this brings us back, once again, to the idea of multiple possible universes. Because if different geometries lead to different particles and constants, then each possible shape of the hidden dimensions corresponds to a different version of physics. Our universe, with its specific laws, may simply be one configuration among many. And yet, within this vast space of possibilities, there is something special about stability. Only certain configurations allow complex structures to form. Only certain combinations of vibrations lead to atoms, molecules, stars, and eventually observers. This does not necessarily mean our universe is unique, but it suggests that it is part of a narrower subset, one where the geometry of hidden dimensions produces a coherent, stable world. Still, the question lingers. Is there a deeper reason why these dimensions have the shape they do? Or is it simply one outcome among countless possibilities? As we continue, we will begin to explore how these hidden dimensions connect to an even broader picture, one where different versions of string theory themselves begin to merge, where seemingly separate ideas reveal themselves as reflections of the same underlying truth. And in that merging, we may begin to glimpse something even more profound, that reality is not defined by a single description, but by many perspectives, quietly connected beneath the surface. As this idea continues to unfold, a quiet realization begins to settle in, one that does not arrive suddenly, but slowly, like a distant thought becoming clearer over time. If the properties of particles emerge from the geometry of hidden dimensions, and if those geometries can vary, then the universe we experience is not the only way reality could exist. It is simply one possibility. This is not just a philosophical statement. It is a direct implication of how string theory behaves, because the equations do not point to a single unique configuration of dimensions. Instead, they allow for an enormous number of consistent shapes, each one producing its own set of vibrations, its own particles, and its own version of physical laws. And so, the universe begins to feel less like a fixed structure, and more like one expression among many. To gently understand this, imagine again the hidden dimensions as tiny, folded spaces at every point in reality. Now imagine that instead of one fixed shape, these dimensions could be arranged in countless different ways. Each arrangement would act like a different instrument, allowing different sets of vibrations, producing different notes of reality. In one configuration, the vibrations might produce particles similar to those we know. In another, the particles might be heavier or unstable, or interact in completely unfamiliar ways. In some configurations, forces might be stronger or weaker. In others, they might not exist at all. Some universes, shaped by certain geometries, might never form atoms. Others might form structures too chaotic to persist. And some, like ours, might settle into a delicate balance, where complexity can emerge and remain stable over time. This leads to a subtle but profound shift in perspective. Instead of asking why the universe is the way it is, we begin to ask why this particular version exists among so many others. And more quietly still, whether there is any deeper reason at all. One possibility is that there exists a hidden principle, something not yet understood, that selects a single geometry from all the possibilities. A rule that determines why the dimensions are shaped in exactly this way, and not another. But so far, no such principle has been clearly identified. Another possibility is more open, and perhaps more unsettling, that there is no single selection, that all these possibilities exist in some broader sense, and that what we call our universe is simply one region within a vast landscape of potential realities. In this view, the laws of physics are not universal in the absolute sense. They are local. They depend on the specific geometry of the hidden dimensions in a given region. And we find ourselves in this particular configuration not because it is uniquely determined, but because it allows for the kind of structures that can observe it. This idea does not necessarily mean that other universes physically exist in a way we could travel to. It may simply mean that the theory allows for them, that they are mathematically consistent possibilities. But even as possibilities, they reshape how we think about reality, because they suggest that what we observe is not the only way things could be. That the constants we measure, the particles we study, the forces we experience, are not inevitable features of existence, but outcomes of a deeper structure that could have taken many forms. And yet, within this vast space of possibilities, there is still a sense of order. Not all configurations are equally stable. Not all allow for complexity. Many may be short-lived, collapsing or fluctuating too quickly to form anything resembling structure. Others may be too simple, lacking the variety needed to build anything intricate. Somewhere within this enormous range, there exists a subset of configurations that are balanced, stable enough to persist, rich enough to evolve, structured enough to support complexity. And our universe appears to belong to that subset. This does not fully answer the question of why, but it reframes it. It suggests that instead of searching for a single predetermined outcome, we may be exploring a space of possibilities, where certain conditions naturally give rise to worlds like ours. As this idea settles, it also prepares us for the next layer of the mystery. Because if there are many possible versions of the universe, there are also many ways to describe the underlying theory itself. Different formulations of string theory have been developed, each with its own structure, its own assumptions, its own perspective. At first, they appeared separate, even incompatible. But as physicists studied them more closely, something unexpected emerged. These different theories were not truly different. They were connected, in ways that suggest they are all reflections of a deeper, unified framework, one that lies beneath them all, just as strings lie beneath particles. And as we move forward, we will begin to explore these different versions of string theory, and the surprising discovery that reality may not have a single description, but many, all quietly pointing toward the same underlying truth. As we move deeper into this quiet unfolding, something begins to feel almost paradoxical. If string theory is meant to describe the fundamental structure of reality, then why does it not come as a single, clear theory? Why, instead, do we find multiple versions, each complete, each consistent, each describing a universe built from vibrating strings, yet differing in subtle and important ways? At first, this seemed like a problem. Physicists discovered not one, but 5 distinct versions of string theory. Each one required extra dimensions. Each one included vibrating strings. Each one was mathematically self-consistent, and yet they differed in how those strings behaved, how symmetries were applied, and what kinds of particles could emerge. It was as if there were 5 different maps, all claiming to describe the same territory. Naturally, this raised a quiet concern. If there are multiple fundamental theories, which one is correct? Are they competing ideas or incomplete fragments of something larger? For a time, no one knew. Each theory had its own internal logic. Some allowed both open strings with endpoints and closed strings forming loops. Others allowed only closed loops. Some treated certain symmetries differently. Some produced different sets of possible particles. They were labeled in ways that sound technical and distant, but behind those labels was a deeper mystery. Why would nature allow 5 separate descriptions of its most fundamental layer? But as physicists continued to explore these theories, something unexpected began to emerge. A pattern, not in the differences, but in the connections. Under certain conditions, one theory could transform into another. Not approximately, but exactly. A theory that appeared completely different at first glance could, under a change of perspective, reveal itself to be mathematically equivalent to another. The particles, the interactions, even the structure of space, all could be mapped from one description to another in a precise and consistent way. This discovery was not just surprising, it was deeply revealing, because it suggested that the 5 theories were not truly separate. They were different expressions of the same underlying reality. To understand this gently, imagine observing a complex object from different angles. From one side, it appears smooth and simple. From another, it reveals intricate detail. From yet another, it may look completely different. But the object itself has not changed. Only your perspective has. In a similar way, these 5 string theories may be different perspectives on a single, deeper structure. What appears as one theory in one context becomes another theory in a different context. And this transformation is not arbitrary. It follows precise mathematical relationships known as dualities. Dualities are a kind of hidden symmetry, a bridge between different descriptions. They reveal that 2 seemingly different theories can produce exactly the same physical predictions, even though they are formulated in completely different ways. In one version, a certain interaction might appear strong and complex. In another, the same interaction appears weak and simple. In one description, space may seem large. In another, the same space appears small. Yet the physics remains unchanged. This challenges something very fundamental about how we think. We are used to believing that there is one correct description of reality. One set of equations, one framework, one way things truly are. But dualities suggest something more subtle. That reality may not have a single description. Instead, it may be understood through multiple perspectives, each valid, each incomplete on its own, but all connected. This is a quiet but profound shift. It suggests that what we call a theory is not necessarily the final truth, but a lens, a way of looking at something deeper. And when we change the lens, the description changes, but the underlying reality remains the same. As this idea began to take hold, physicists started to suspect that all 5 string theories were not the final answer, but pieces of a larger puzzle, fragments of something more fundamental, something that could unify them all. And slowly a new idea began to form, that beneath the 5 theories, beneath their differences and connections, there exists a deeper framework. Not a theory of strings alone, but something that includes strings and more. Something that lives in a higher dimensional space, where the distinctions between these theories dissolve. This idea would eventually be called M-theory. But at this point in our journey, it remains only a hint. A suggestion that the 5 different faces of string theory are not contradictions, but reflections. That the universe may not be described by a single equation, but by a network of interconnected perspectives. And that somewhere within this network, there is a deeper unity waiting to be understood. In the next segment, we will begin to explore these dualities more closely, and how they reveal that even concepts like size, distance, and strength may not be absolute, but relative, depending on how we choose to look at reality. As we gently arrive at the final layer of this part, something begins to feel almost unfamiliar. Not because it is complex, but because it quietly challenges one of our deepest assumptions. The belief that reality has one true description. For most of science, this assumption has guided everything. We search for the correct equation, the final theory, the single framework that explains all things. But as string theory unfolds, and as these dualities reveal themselves, that certainty begins to soften. Because what we find is not one theory, but many. And more importantly, we find that these many theories are not in conflict. They are equivalent. This is where the idea becomes both subtle and profound. 2 descriptions of reality can look completely different. They may use different concepts, different objects, even different dimensions. And yet, when carefully examined, they produce the same physical outcomes, the same predictions, the same observable universe. It is as if reality is allowing itself to be described in multiple ways, each one valid, each one incomplete on its own. To understand this more intuitively, imagine describing a landscape. One person may describe it in terms of color and light, the softness of shadows, the warmth of the sky. Another may describe it in terms of geometry, distances, angles, shapes. A third may describe it through sound, the quiet movement of wind, the distant echo of space. Each description captures something real, but none of them on their own fully contain the landscape. In a similar way, the different string theories appear to be distinct, but they are simply different ways of describing the same underlying structure. And the bridges between them, these dualities, reveal something deeper. They suggest that concepts we once believed to be absolute are not. Take distance, for example. In everyday life, distance feels fixed. A large space is large. A small space is small. But in certain string theory dualities, a universe with a large dimension can be mathematically equivalent to one with a very small dimension. What appears vast in one description becomes compact in another, yet the physics remains unchanged. This is not just a trick of perspective. It suggests that size itself may not be fundamental. Similarly, the strength of interactions, what we call forces, can also transform. A theory where interactions are extremely strong, difficult to calculate and understand, may have an equivalent description where those same interactions are weak and simple. This means that what appears complex in one framework becomes simple in another, and what appears simple may hide complexity beneath. This inversion of perspective is one of the most powerful aspects of duality. It allows physicists to study problems that would otherwise be impossible. But beyond its practical use, it carries a deeper message: that reality does not belong to a single viewpoint. It can be approached from multiple directions, each revealing different aspects, each necessary to build a more complete understanding. As this idea settles, it begins to dissolve the boundary between theories. The 5 string theories are no longer separate candidates competing for truth. They are interconnected, woven together through a network of relationships. And this network hints at something beyond itself, a deeper structure, one that contains all these perspectives as special cases. This is where the idea of a more fundamental theory begins to emerge. Not a theory that replaces the others, but one that includes them, unifies them, explains why they are all connected. A theory where strings are not the only fundamental objects, where higher dimensional structures also play a role, where the distinctions between different formulations disappear, because they are all expressions of the same underlying reality. This is the quiet beginning of what is called M-theory. But before we step into that final layer, there is something important to pause and feel. Because what we have uncovered so far is not just a new model of physics. It is a shift in how we think about truth itself. The idea that there may not be a single ultimate description, but rather a collection of perspectives, all pointing towards something deeper, something that cannot be fully captured in one frame. It suggests that understanding the universe is not about finding one perfect answer, but about learning how different answers connect. And as we move into the final part of this journey, we will explore what lies beneath these connections, the emergence of a higher dimensional framework, the possibility that strings are only part of a larger picture, and the quiet, humbling idea that reality itself may be far more fluid, more interconnected, and more mysterious than we ever imagined. Before we drift into that final part, if you are still listening, gently let me know by typing 2 in the comments. As we begin this final descent into the deepest layer of the mystery, something gently shifts once more. Up until now, strings have been at the center of everything. They replaced particles, explained forces, and revealed hidden dimensions. But as physicists followed the implications of string theory further, they encountered something unexpected. Strings may not be the final layer. They may be part of something even larger. This realization did not arrive all at once. It emerged slowly through the study of dualities, through the connections between different theories, and through a quiet observation. Under certain conditions, strings begin to behave in ways that cannot be fully explained if they are the only fundamental objects. In particular, when the strength of interactions increases, when the system moves beyond gentle, small fluctuations, new structures begin to appear. These structures are not one-dimensional like strings. They are higher dimensional. They stretch across surfaces of volumes, extended regions of space. They are sometimes described as membranes or more generally as branes, objects that can have multiple dimensions. A one-dimensional string is just the simplest case. But in this deeper picture, there may exist two-dimensional surfaces, three-dimensional volumes, and even higher dimensional entities, all part of the same fundamental framework. At first, this might feel like a complication, as if the simplicity of strings is being replaced by something more complex. But there is another way to see it. These objects are not separate additions. They are natural extensions. Just as a point can extend into a line, and a line into a surface, strings may be part of a broader family of objects, all connected, all governed by the same underlying principles. And it is within this broader picture that a new idea begins to take form, that the true fundamental theory of reality is not just about strings, but about all these extended objects together. This is where the concept of M-theory begins to emerge, not as a fully defined theory, but as a unifying framework. A deeper layer that contains all five string theories, all their dualities, and all these higher dimensional objects as different aspects of a single structure. In this framework, strings are no longer the only building blocks. They are one type of excitation among many. In some situations, they dominate. In others, these higher dimensional branes become more important. And depending on how we look at the system, what we perceive as a string in one description may appear as a higher dimensional object in another. This is a continuation of the idea we encountered earlier, that reality does not have a single description. It reveals itself differently depending on perspective. But M-theory takes this even further. It suggests that the number of dimensions in the universe may not be fixed at 10, as in traditional string theory, but may extend to 11. An additional dimension, not visible in ordinary conditions, but emerging under certain circumstances. This 11th dimension is not just an extra direction. It is a doorway into a more complete picture. In some interpretations, what we perceive as strings in 10 dimensions are actually slices or projections of higher dimensional objects moving through this 11-dimensional space. What appears simple from one viewpoint becomes richer and more complex when seen from another. This idea gently transforms how we think about dimensions themselves. They are no longer just coordinates, fixed directions in space. They may be dynamic, emerging, or becoming visible depending on the energy, the scale, or the configuration of the system. At low energies, we experience a familiar world. 3 dimensions of space, 1 of time. But at deeper levels, additional dimensions may unfold, revealing structures that are normally hidden. And within these structures, the distinctions between strings and branes begin to blur. They are no longer separate categories. They are part of a single continuum. This is where the narrative becomes almost philosophical. Because if strings are not fundamental, and branes are not fundamental, then what is? What lies beneath them? M-theory does not yet provide a complete answer. It is still incomplete. Its full mathematical formulation is not yet known. It is understood through fragments, through approximations, through connections between different theories. And yet, despite this incompleteness, it offers a powerful suggestion that the universe at its deepest level may not be built from objects at all. Not particles, not strings, not even brains, but from relationships, from patterns of interaction, from geometry, from connections that give rise to everything we observe. This is a subtle shift. It moves us away from thinking of reality as a collection of things, and toward thinking of it as a network of relationships. A dynamic structure where what exists is defined not by what it is, but by how it connects. As we continue into the next segment, we will explore how this deeper framework reshapes our understanding of space, time, and even existence itself, and how the idea of an 11th dimension opens the door to a reality far beyond anything we can directly perceive. As we continue drifting deeper into this final layer, the idea of an 11th dimension begins to take on a quiet and almost dreamlike significance. It is not simply another direction added to space, like adding one more axis to a graph. It is something more subtle, something that changes how all other dimensions relate to each other. In earlier parts of our journey, we imagined extra dimensions as being curled up, compact, and hidden at every point in space. Tiny structures shaping the vibrations of strings. But now, with the emergence of this higher framework, something begins to shift. This additional dimension does not always remain hidden. Under certain conditions, it reveals itself. This is one of the most intriguing aspects of M-theory. At low energies, when everything is calm and stable, the universe appears to have 10 dimensions in the string framework. But as the energy increases, as interactions grow stronger, an extra dimension seems to open, as if reality itself is unfolding into a larger space. It is not that the dimension suddenly appears from nowhere. It was always there, but inaccessible, compressed into a form that only becomes visible when the system is viewed from a deeper perspective. This idea gently challenges how we think about space. We tend to imagine dimensions as fixed, either present or not. But here, dimensionality becomes something more fluid, something that can emerge depending on conditions, something that is not absolute, but relational. To understand this more intuitively, imagine looking at a shadow on a wall. From one angle, it appears flat, two-dimensional. But the object casting the shadow exists in 3 dimensions. The extra depth is not visible from that perspective, yet it is always there, shaping what you see. In a similar way, the universe we perceive may be like a shadow, a lower dimensional projection of a richer, higher dimensional structure. And the 11th dimension is part of that hidden depth. Within this expanded space, the behavior of strings begins to change. What once appeared as a one-dimensional object may now be understood as a slice of something larger, a higher dimensional surface moving through this deeper space. This leads to a quiet unification. Strings and brains, once thought of as separate, become aspects of the same underlying reality. Different expressions of objects that exist in higher dimensions. And as these objects interact, intersect, and evolve, they give rise to the phenomena we observe: particles, forces, even the structure of space and time itself. But this raises a deeper question. If dimensions can emerge, if objects can change their nature depending on perspective, then what is truly fundamental? Is there a lowest level, a final building block? Or is reality something more fluid, something that does not have a single foundation, but instead unfolds through layers of description? M-theory does not yet provide a complete answer, but it suggests something quietly profound, that the universe may not be built from fixed ingredients. Instead, it may be built from processes, from transformations, from relationships, from patterns that shift depending on how they are observed. In this view, space itself is not a rigid container. It is dynamic, can stretch, fold, and even change its dimensional structure. Time is not just a background parameter, but part of this evolving geometry. And objects, whether particles, strings, or brains, are not isolated entities. They are excitations, movements within this deeper structure. This perspective dissolves many of the boundaries we are used to. The boundary between dimensions, between objects, between different theories. Everything becomes part of a continuous whole. And within this whole, the 11th dimension acts like a bridge, connecting different descriptions, allowing transitions between what once seemed separate. It is as if reality has layers, and by shifting our viewpoint, we move between them. At one level, we see particles, at another, strings, at another, brains, and beyond that, something still deeper, not yet fully understood. This brings us gently toward a final reflection, because as the structure of reality becomes more fluid, more interconnected, more dependent on perspective, we begin to sense that our usual way of thinking may be limited. We look for solid foundations, fixed truths, ultimate answers. But what if reality is not built that way? What if it is more like a tapestry, woven from relationships, where no single thread defines the whole? In the next segment, we will explore how this idea reshapes not just physics, but our understanding of existence itself. How the universe may not be made of things, but of connections. And how, at the deepest level, what we call reality may be something far more subtle and far more peaceful than we ever imagined. As we move further into this quiet unfolding, something begins to soften at the very core of how we understand existence. Up until now, even as particles dissolved into strings and strings into higher dimensional objects, there was still an assumption gently holding everything together, the idea that somewhere, at some level, there must be a final thing, a smallest unit, a true foundation. But what begins to emerge here is something more subtle. What if there is no final object at all? What if the universe is not built from things, but from relationships between things? This idea does not arrive suddenly. It grows slowly from everything we have already explored. If particles are just vibrations, and those vibrations depend on geometry, and that geometry depends on deeper structures, and those structures change depending on perspective, then the idea of a fixed, independent object begins to fade. Nothing exists entirely on its own. Everything is defined by how it interacts, how it connects, how it relates. In this view, a particle is not a self-contained entity. It is a pattern of interaction, a stable relationship within a network of vibrations. Its properties are not inherent, but emerge from how it fits into the larger structure. Even space itself begins to feel less like a backdrop and more like a web of relationships. Distance is not just separation. It may be a measure of how strongly things are connected. Time is not just a flowing line. It may be a sequence of changes within this network. And what we perceive as reality is the surface of this deeper, interconnected system. To gently imagine this picture a vast, invisible web, not made of physical threads, but of connections. Points in this web are not fixed objects, but nodes, places where relationships converge. The strength and pattern of these connections define everything we observe. A stable cluster of connections appears as a particle. A changing pattern appears as motion. A large-scale structure of connections appears as space itself. In this way, the universe becomes less like a collection of building blocks and more like a living pattern. This idea resonates quietly with what M-theory suggests, that beneath strings and brains, beneath dimensions and geometry, there may be something even more abstract, a structure defined not by objects but by relationships. And this structure may not have a single fixed description. Instead, it can be viewed in different ways, each revealing different aspects. One perspective highlights particles, another highlights strings, another reveals higher dimensional surfaces. None of these are wrong, but none are complete. They are different windows into the same underlying reality. This is where the concept of duality becomes more than a mathematical tool. It becomes a hint that reality itself is flexible, that what we see depends on how we look, and perhaps more gently, that there is no single correct way to describe the universe. Only different perspectives, each capturing part of the whole. This can feel unsettling at first. We are used to seeking certainty, to believing that somewhere there is a final answer, a definitive description. But here, the answer seems to dissolve into a network of possibilities. And yet, there is something peaceful in this, because it suggests that reality is not rigid, not fixed, not confined to a single framework. It is open. It allows multiple views, multiple descriptions, multiple ways of understanding, all connected beneath the surface. As this realization settles, another quiet thought begins to emerge. If everything is defined by relationships, then nothing is truly isolated. Every particle, every force, every structure is part of a larger whole, a pattern that extends beyond what we can directly perceive. Even we, as observers, are not separate from this system. We are patterns within it. Our thoughts, our perceptions, our awareness are themselves part of this network of relationships. Not outside observers, but participants. This does not diminish our place in the universe. It deepens it. It suggests that understanding reality is not just about observing from a distance, but about recognizing our connection to the whole. And in this quiet recognition, the boundary between observer and observed begins to soften. As we approach the final segments of this journey, we will begin to slow down, to reflect, and to gently bring together everything we have explored. From particles to strings, from strings to dimensions, from dimensions to deeper structures, and finally, to the idea that reality itself may be a web of relationships, endlessly unfolding. As we begin to approach the end of this long, gentle journey, something subtle starts to happen. The ideas we've explored no longer feel separate. They begin to blend together: particles, strings, dimensions, dualities, and relationships, all becoming part of a single quiet picture. And in that picture, one realization slowly becomes clear. The reality we experience may not be what it seems, not in the sense that it is false, but in the sense that it is incomplete. A surface, a simplified version of something deeper and far more intricate. We began with particles, tiny points that seemed to form everything. Then those points dissolved into vibrating strings. Those strings revealed hidden dimensions. Those dimensions unfolded into multiple possibilities. And those possibilities connected through dualities into a deeper framework. And now, even that framework begins to soften, because what we are left with is not a final object, not a final theory, but a quiet sense that reality itself is layered. What we perceive is one layer. What physics describes is a deeper layer. And beyond that, there may be layers we do not yet have the language to describe. This does not mean that the world around us is unreal. The stars, the ground beneath you, the rhythm of your breath, all of it is real in its own way. But it may not be fundamental. It may be emergent, a stable pattern arising from deeper processes, much like a wave on the surface of an ocean. The wave is real. It has shape, motion, presence. But it is not separate from the water beneath it. It is a pattern, not a thing. In the same way, everything we experience may be patterns, stable, persistent, meaningful, but not independent. This idea gently dissolves the solidity of the world, not in a frightening way, but in a calming one, because it suggests that change is not a disruption, but a natural part of the underlying structure. That what appears fixed is actually dynamic. That stability is not permanence, but balance. Even space and time, the stage on which everything unfolds, begin to feel less absolute. They may not be fixed containers, but flexible aspects of a deeper system. They can stretch, bend, emerge, and even disappear under certain conditions. And if that is true, then the boundaries we rely on between here and there, now and then, object and observer begin to soften. This is where the journey becomes less about physics and more about perspective. Because what we are really exploring is not just what the universe is made of, but how we understand it. We are used to thinking in terms of objects, things that exist independently, that have properties that interact. But what if this way of thinking is only useful at a certain level and begins to break down as we go deeper? What if reality at its core is not made of things, but of patterns and relationships. This is not an answer, but a direction, a quiet shift in how we look. And as we sit with this idea, something else begins to emerge. A sense of unity, not in the sense that everything is the same, but in the sense that everything is connected, that what appears separate is part of a larger whole, that differences arise from perspective, from how patterns are arranged, from how relationships are structured. And within that whole, there is no clear boundary where one thing ends and another begins. Only transitions, only transformations, only movement within a deeper structure. This can feel abstract, but it also carries a quiet simplicity, because it suggests that the universe is not something distant, not something separate from us, but something we are part of. We are not outside observers looking in. We are patterns within the same system. Our thoughts, our awareness, even the act of listening right now, are part of this unfolding structure. And in that sense, the mystery is not just out there, in distant galaxies or hidden dimensions. It is also here, in the simple fact of experience. As we move into the final segment, we will allow everything to slow down. No new concepts, no new layers, just a gentle reflection on what we've explored, and a quiet return to stillness, carrying with us the sense that beneath everything, there is something deeply connected, quietly vibrating, endlessly unfolding. And now, as we reach the quiet end of this journey, there is nothing more to solve, nothing more to unravel, only something to gently feel. Because what began as a question about particles slowly opened into something much wider. A shift from solid objects to vibrating strings, from strings to hidden dimensions, from dimensions to vast possibilities, and finally, into something even softer, a universe not made of things, but of patterns, of relationships, of quiet connections unfolding beneath everything. And perhaps the most peaceful part of this realization is this: nothing we experience is separate from that deeper structure. The ground beneath you, the air around you, the distant stars, and even the quiet rhythm of your own breathing are all part of the same unfolding pattern. Not isolated pieces, but expressions of something shared, something continuous, something that does not begin or end at clear boundaries, but flows gently through everything. In this view, the universe is not something rigid or mechanical. It is not a collection of parts assembled together. It is more like a slow, ongoing process, a kind of cosmic unfolding, where patterns emerge, evolve, and dissolve, all within the same underlying fabric. And within that fabric, everything is connected. Not in a dramatic or overwhelming way, but in a quiet, almost invisible way. The kind of connection that does not need to be seen to be present. The kind that simply is. And as you rest here, listening, perhaps you can imagine it softly, not as a complex theory, not as equations or dimensions, but as a gentle idea, that beneath everything, there is a kind of stillness, a calm structure, endlessly vibrating, endlessly shaping what appears, and then letting it fade. The stars you see in the night sky are patterns in that structure. The atoms that form your body are patterns in that structure. Even your thoughts, drifting in and out of awareness, are patterns too. Nothing separate, nothing fixed, just movement within something deeper. And yet, despite this constant motion, there is a sense of balance, because patterns can be stable, they can persist, they can form shapes that last long enough to be experienced, to be felt, to be understood, even if only partially. And that is where we find ourselves, within one of those patterns, a small, quiet part of a much larger unfolding. Not needing to understand all of it, not needing to see every hidden dimension or every possible universe, but simply existing within it as it gently continues. There is something calming in that, because it means that not everything needs to be known. Not everything needs to be resolved. The mystery itself is part of the experience. And perhaps that is what makes it meaningful. That the universe is not just something to explain, but something to slowly explore, to gently feel, to rest within. So as this journey comes to a close, there is no final answer waiting. Only a quiet perspective that reality may be far deeper than it appears, far more connected, far more subtle, and far more peaceful than we often imagine. And as you begin to drift, letting these ideas soften, letting them fade gently into the background, you can carry with you a simple thought, that beneath everything, there is a quiet rhythm, a vibration, steady and continuous, shaping all things without ever needing to be seen. And you, in this moment, are part of it. If you're still here, still listening in this calm space, gently let me know by typing 3 in the comments. And now, you can simply rest as the universe continues quietly, endlessly around you.